This video covers the propulsion page of the ACEP Premium Access portal. The page presents the propulsion system as a sequence of functional stages, spanning fuel storage and distribution, reactor core operation, and magnetic nozzle thrust generation and vectoring. This structure allows the propulsion chain to be examined as a single, continuous physical process along the mission trajectory. The fuel and feed panel presents the real-time state of propellant storage, conditioning, and delivery, showing how reaction mass and auxiliary fuels are routed, metered, and supplied to the reactor cores, magnetic nozzle, maneuver thrusters, and supporting subsystems. Fuel reserves are shown as dedicated tanks for proton-boron 11 reaction mass, anti-proton supply, and metallic hydrogen. Each tank displays remaining fraction, cumulative usage, arrival reserve estimate, internal pressure, and temperature. The proton-boron 11 tank represents the primary reaction mass store for fusion operation. Its telemetry additionally includes isotopic enrichment and short-term feed stability, which together constrain achievable fusion efficiency and ignition repeatability. The anti-proton tanks, assigned independently to reactor cores 1 and 2, provide catalytic injection for ignition and burn stabilization. The MAG parameter reports the confinement field in Tesla and serves as a direct proxy for anti-proton confinement margin and safe pulse scheduling. The metallic hydrogen tank supplies auxiliary propellant and thermal energy. It supports plasma conditioning, neutral beam injection, maneuver thrusters, and the MHCS. The reactor core symbols mark the delivery endpoints of all primary fuel paths. Fuel routing and feed lines visualize connections between tanks, injectors, cores, thrusters, and auxiliary systems. Line color and animation indicate fuel type and flow state, while associated data fields report instantaneous flow rate, pressure, temperature, and short-term stability. The annunciator strip summarizes injector availability and subsystem engagement. Illuminated indicators confirm active units. The maneuver thrusters represent discrete metallic hydrogen consumers used for significant attitude changes. Their status symbols indicate readiness and firing state. The MHCS, the metallic hydrogen combustion system, reports availability for post-arrival power generation and transitional thermal support. The fuel status and contribution panel presents the temporal evolution of propulsion fuel inventories and their instantaneous contribution to the exhaust mass flow. Fuel remaining is plotted as a percentage of initial load versus mission proper time, while current mixture share indicates the relative contribution of each fuel to propulsion at the present operating point. The DCMCAAFR panel presents a cross-sectional diagnostic view of the dual-core magnetically confined anti-proton augmented fusion reactor. It visualizes the physical geometry, operating state, and symmetry of reactor cores 1 and 2, together with their magnetic confinement systems and active fuel coupling. Each reactor core is shown with its plasma volume, confinement boundary, and injector interfaces, providing a spatial reference for fusion power generation and fuel deposition. The two cores operate in coordinated but independently controlled modes, allowing fine load balancing, thermal management, and redundancy during sustained propulsion. The core load indicators report the instantaneous power contribution of each core relative to total plant demand. These values define how propulsion power is distributed between cores and how closely the system is operating to single-core or dual-core limits. The core balance indicator shows the differential load between core 1 and core 2. Small offsets are nominal and are used to manage magnetic stress, plasma stability, and component lifetime, while larger deviations indicate corrective action or protective constraints. The plasma confinement geometry depicts the real-time magnetic shaping and stability state of each reactor core. The overlaid boundaries and field contours correspond to physically meaningful plasma parameters, including elongation, triangularity, edge positioning, and confinement symmetry derived from standard fusion diagnostics. These elements are continuously updated and respond dynamically to changes in magnetic field configuration, injector timing, auxiliary heating, and load redistribution required to maintain steady fusion conditions. The injector overlays identify which fuel and auxiliary channels are actively coupled to each reactor core and their current operational role. Proton-boron 11 injectors provide the primary fusion reaction mass, while anti-proton injection supplies catalytic ignition and burn stabilization. Metallic hydrogen is used for plasma conditioning, auxiliary heating support, and as feedstock for neutral beam injection, which contributes to plasma heating, current drive, and confinement shaping during startup, transients, and controlled load transitions. Together, these overlays allow direct correlation between fuel delivery strategy, plasma response, and reactor output across steady state, ramp up, ramp down, and contingency operating regimes. The coil health matrix represents continuous diagnostic sampling of the magnetic confinement system at the level of individual coils. Each coil is periodically and pseudo-randomly evaluated across 3 dimensions: magnetic field stability, thermal margin to quench, and current balance relative to commanded load. This distributed sampling strategy avoids correlated stress artifacts and provides early detection of localized degradation before it propagates into global confinement loss or stability constraints. The test single-core operations control triggers a diagnostic visualization of single-core reactor operation. It temporarily renders the propulsion system as if only one reactor core were active, without modifying live telemetry, control laws, or propulsion state. This mode is provided for operator familiarization with single-core load distribution, geometry, and subsystem coupling, reflecting the inherent redundancy of the dual-core architecture. At mission phases where total propulsion demand falls below 50% of rated reactor output, a single core is sufficient to sustain nominal operation, allowing continued flight with full subsystem availability in the event of a single-core critical anomaly. The DCMCAAFR Summary panel presents the reactor state as a compact numerical snapshot organized by physical domain. Parameter placement is governed by operational efficiency and rapid interpretation, allowing an operator to assess consistency and margin without reading the panel linearly. Core load and fusion power values describe how total propulsion demand is shared between cores 1 and 2, and how closely the system is operating to single-core or dual-core limits. These values establish the overall thrust production regime and available redundancy. Plasma thermodynamic parameters, including ion and electron temperature, density, pressure, and stored energy, characterize the internal energy state of each core and confirm operation within the expected fusion regime. Magnetic confinement and stability parameters define proximity to known operational limits. Plasma current, magnetic field strength, confinement time, beta values, safety factor, and related metrics collectively describe confinement quality and stability margin. Exhaust and diverter parameters quantify how fusion power is extracted and converted into directed exhaust. Exhaust mass flow, diverter load fraction, and heat flux indicate whether propulsion coupling remains efficient while maintaining acceptable thermal conditions at plasma-facing components. Fuel and auxiliary input parameters show how much external support is required to sustain the current operating point. Proton-boron 11 feed rate, anti-proton coupling, metallic hydrogen usage, and neutral beam injection power indicate the degree of augmentation needed for stability, ignition support, and controlled transitions. Global hardware margins summarize absolute operating headroom, maximum coil temperature, quench margin, and composite stability indicators define non-negotiable limits that override all other considerations if approached. Together, these parameter groups allow the reactor state to be interpreted as a rapid assessment of propulsion performance, stability margin, and long-term operational sustainability. The mag nozzle panel presents a longitudinal cross-section of the magnetic exhaust nozzle and its active control state. The magnetic nozzle converts reactor plasma energy into directed exhaust momentum by magnetically expanding, collimating, and detaching the plasma flow, enabling efficient thrust generation without material contact. The central plasma path visualizes the guided exhaust stream from the reactor interface through compression, reconstriction, and final expansion. Field geometry controls plume shape, divergence, and detachment location, allowing thrust magnitude and direction to be regulated through magnetic shaping rather than mechanical structures. Axial station indicators report thermal and pressure conditions at 3 characteristic nozzle locations. These values describe how energy and momentum are redistributed along the nozzle and provide early indication of overexpansion, underexpansion, or detachment drift that would reduce axial efficiency or increase structural load. Vectoring effects are visible as controlled asymmetry in the plasma path. Small, symmetric deviations correspond to routine attitude control, while sustained asymmetry reflects deliberate thrust steering at the cost of increased divergence and localized thermal stress. Surrounding coil structures represent the magnetic elements responsible for confinement, compression, trimming, and vector control. Their arrangement defines the effective expansion ratio and the achievable range of thrust vector deflection. The coil health matrix applies the same diagnostic logic used for the reactor confinement system. Individual nozzle coils are periodically and pseudo-randomly evaluated for magnetic field stability, thermal margin to quench, and current balance relative to commanded load. This sampling strategy provides early detection of localized degradation before it propagates into global loss of nozzle efficiency or vectoring authority. Animated dashed lines along the nozzle walls indicate active coil cooling and heat extraction paths, visualizing how resistive and intercepted thermal loads are routed away during sustained thrust. Together, these elements describe the instantaneous state of exhaust formation, thrust efficiency, and steering capability, linking reactor output directly to controlled spacecraft acceleration. The mag nozzle performance and vectoring panel provides a quantitative summary of exhaust generation, thrust efficiency, and steering behavior derived from the magnetic nozzle state. The polar vector display shows the commanded exhaust deflection relative to the ship axis. Angular position encodes thrust direction, while radial offset represents vector magnitude, allowing rapid assessment of steering effort and correction authority. Numerical readouts report reactor plant power delivered to propulsion, kinetic power carried by the exhaust, required thrust for the current vehicle mass, exhaust mass flow, effective exhaust velocity, and resulting specific impulse. Together, these values define the instantaneous propulsion efficiency and momentum coupling. Plume geometry parameters, including half-angle and divergence loss, quantify how effectively exhaust momentum is aligned with the thrust axis. The comparison between ideal exhaust thrust and axial thrust reflects losses introduced by vectoring and plume spread. Axial station temperatures and pressures describe the thermodynamic evolution of the plasma along the nozzle and provide context for expansion efficiency and detachment behavior. Exit Mach number and specific kinetic energy characterize the exhaust flow regime at discharge. Attitude-related readouts report yaw, pitch, and roll relative to the thrust axis. together with the resulting lateral accelerations generated by small vector offsets. These values link nozzle vectoring directly to spacecraft attitude control. Summarizing, the propulsion page presents a complete, internally consistent view of how stored mass and energy are converted into controlled thrust, steering authority, and sustained acceleration along the mission trajectory.